some problems today with Studios, with one of the Hortus servers. So I did send the email, I did send the Zoom link to all the people whose email I had. There are some people whose email I don't have, or who sign in, who have the email handle such that I don't recognize it as a student of mine. So people who figure out, who invent some pseudonyms and fake names for their email accounts suffer from this. So they might think about that. But of course, people who are here evidently did receive the Zoom link. And that means that also I see, okay, I see people whom I haven't seen for ages here online. That's interesting. All right, so today we are working with special limits. We were discussing some traditional limits, more or less, and now today we will have two kinds of very special limits, and those would be generally limits where the traditional methods divide something out, do this, do that, might not work, and so we would need to do something somewhat different. So,
Miss, I have a question.
Yes.
Did you mark our retake 3?
No, not yet. No, not yet.
Okay.
I told you last week I was very, very busy. This is the examination time for everybody. So many people are writing final examinations already. Other groups are writing final examinations. And I have an entrance examination. I will mark them when I have found time to do that. I'm marking all the time.
Okay, sure, miss, sure. And miss, for you, when do you know when will we finish this unit, and when will be the test for this unit?
The test for this unit is going to be, okay, I'll talk about that hopefully in a while when more people show up, because at the moment I only see there's 26 of you, something like. So I don't want to repeat this, but next week is going to be special because we have lectures moved, 3 days moved, and so on and so on. So I'll talk about it a bit later towards the end.
Okay, sure.
Excuse me, miss.
Excuse me, miss. Yes.
Miss, I didn't get your email, so what should I do?
What do you mean you didn't get my email?
Yeah, I joined this class using my friend's link from my friend.
You did not get my email, evidently, because if you have ever emailed me, then it has been from some strange email address that I don't recognize. I sent email to all the addresses that I could recognize as address of a student. So that means my Gmail address book did not recognize your address as yours. I was going through the student list, my basic student list. So in fact, when you email me, you must make sure, first of all, that the name that you put in your account and your email address is your name, because otherwise it might create difficulties. I was going through the list. I was typing in the beginning of your name or one of your many names. I tried several for many people. As long as I got something out of that that I could recognize as your address, I did it. But the problem with many of you is that your email address is evidently a private email address, and you are using it for work and for study purposes, and it's not always recognizable. So
I'm using my Outlook email for which I got from university.
Well, I can't say because I use what I have. I use what I have. And so let me just check. I think I wanted to see chat. Yes, I wanted to see this in case somebody says something, types something in the chat that I need. All right. So then we go with the limits. I will talk about the organizational issues later in this lecture, a little bit later, so that people who tend to be late, as always, could hear that, could listen to this. And so we dealt with limits that actually had polynomials or radicals. In other words, algebraic expressions. Yes, we had some exponential limits, well, one or just a few to consider, knowing the behavior of the exponential function. But the main problem is that we also have, for example, limits with trigonometry, for instance. And if we don't have some basic issues with these, if we don't have something important to, let's say, to tell us how to deal with these limits, then we might be stuck. And so the first limit is sine x ratio to x. Sine x divided by x when x tends to 0. We see when x is 0, what we have is sine of x is also 0. Sine of 0 is 0. So we basically have 0 over 0, which is, let's say, an indeterminate form. So this is something that, for example, cannot be resolved in the previous way, the way we discussed last time. So in principle, what we will do, we will consider a little bit of graph. So what we have here in this graph, okay, let me get my pen. So we have, let's say, the trigonometric circle. Let's suppose this is the trigonometric circle, unit circle. We have 1 and 1. And basically, when we measure angles in radians, and we have a unit circle, then basically x radians means the length of the arc corresponding. If this is the angle x, then the arc length is x units. If angle is x in radians, then the arc length is x units, because we are working with a trigonometric circle. That's from the definition of radian. We will start discussing trigonometry in elementary mathematics next week. So 1 radian, by definition, was the angle whose corresponding arc length is equal to the radius. And since the radius is 1, then in the unit circle, the arc of 1 radian would be 1 unit long, and the arc of x radians would be x units long. So we, at this point here, we are discussing here the length of the arc, which is x in our case. And the sine value of this angle, of course, is this, the vertical segment. And of course, we see that these are, well, not exactly the same. Now, if we decide to take a smaller angle, in other words, remember that our angle tends to 0. So if I take a smaller angle, this would be the arc length, this would be the arc length, and this would be the sine value. So they are a bit closer. If I take an even smaller angle, you see how close the arc length and the sine value, these two, the segment and the arc, become very, very close. They become generally very, very close in size. And therefore, we actually conclude that the sine x to x, the limit when x tends to 0, this limit equals 1. This limit equals 1. So you see that for comparatively larger sine values, it's not the same. It's not actually true, as we see in the original picture. But as x becomes very, very small, then we can say that, all right, the radius, this is the arc length, and this is the sine. You see, they are almost the same. And from that, roughly, we can conclude that this ratio equals 1. However, this is not the perfect proof. A perfect proof would take a bit more time. I will skip that at the moment. It can be proved, it's not really difficult, but it would take up, let's say, some minutes, and we don't have that much time. What with the online work and online tests and everything, we are basically spending more time working than it would be normally in the classroom. So let's consider just some examples. So what is this good for? Okay, so we have one limit. So what? Now, what can we do with this? Is it simply for one situation? And let's have a look at some examples. For example, if we have a limit like sine x divided by 3x, we can evidently quite easily take 1/3 out of the limit, and then inside the limit we still have sine x divided by x when x tends to 0, which is 1. So it's 1/3 times 1, and that is 1/3. Simple enough. Simple enough. That's because the coefficient 1/3 is not inside. It's not anywhere inside my limit, inside my expression. Really, I see the limit very clearly. Sometimes I even do this, and I will do this quite a lot today. I simply mark, okay, this limit is 1. This expression tends to 1. And so 1/3 times 1 is 1/3. That was easy. Now the next situation, sine of 8x divided by 5x. Now what do we do? The thing is that, is it just 1? Is it something else? We could multiply it by, no, we don't multiply it by 3, divided by 3, because that doesn't help. We see 1/3 is clearly a coefficient. We can bring it outside. That is not a problem. The problem is that here, this multiplication by something and dividing by something, yes, it will be helpful. It will be very helpful in my second example. So what we should remember is that the limit actually applies to, okay, this had to be t, I'm sorry, this had to be t. This had to be t, the angle inside, as long as you see that the expression inside sine and outside, so this and this, as long as you see that these are equal, and both tend to 0, of course, then we can say that this limit is 1. In that case, we could say that this limit is indeed equal to 1. I think I have to return the white. Yes. This limit is indeed equal to 1. In this case, we see that, no, but we don't have equal. We don't have sine of something divided by that same something. We cannot change 8 inside the sine. For trigonometry, inside the sine, it's very difficult to change the argument, the independent variable inside sine. And therefore, we change the value outside, we change the opposite value. So in principle, some people know how to do this. Some people know the general idea. So I'm going to show something very, very simple, a very simple approach that will help. So we multiply, we could multiply by 5/5 this time, or for some people for whom it might be slightly difficult to understand, there are some people evidently who do see limits for the first time. Not all school programs, not all school syllabi actually use limits and these finer limits, these detailed things. So we can, in this case, for sine of 8x, we need 8x in the denominator. We would need 8x. So mathematicians are often like this. We don't have it, so okay, let's write it where we need it. But then, of course, we need to compensate. We have been doing this previously. For example, when you are completing the square, remember, you add the third term inside parentheses, but then you have to compensate for it. You have to cancel it out again. Similarly, in this case, yes, it can be done in a little bit more simple manner. It could be done. It could be done like that. Okay. Right. But simple. If I say sine of t in some expression, sine of something, I could just take this something. I could just take this something and write it where I need it, because then I would have this limit. But of course, if I divide by it and it's not really there, then I also need to multiply it. So now I say, or think to myself, all right, this is 1. This limit is 1. And so what remains? And so what remains is simply, evidently, the limit of 8x to 5x. Yes, I know it can be done faster. So x and x cancel out, and so we have the limit value 8/5. In many cases, again,
Miss,
yes.
but it's easier to understand if you just like show that how like sine 8x is always multiplied by 1, right? Because it's just sine 8x. So we could just make the 1 as 8 divided by 8 is already 1. And so that's how it's cancelled out. That's the easier way to understand it, right?
I would still need you to show some working. Just plopping down the answer doesn't work for example, for testing.
No, I didn't mean like that. So like, I mean like.
There are many methods to do this. And if you see an example and you know the answer immediately, that's perfectly fine. That's wonderful. It's just that you need to show something in between.
I meant like sine 8x is also same as so like so let's x is also equal to sine 8. Dot 1, right?
That's right.
Sine 8x is also equal to 8 divided by 8. That's the easier way to understand, right?
That's what we do quite often. This is basically almost the same I did. I multiplied by 8 and divided by 8. It's just that I attached.
Because what makes it confusing is the x. Like, why did you use the x as well?
Yes. That's right. But the thing is that for some people, it's easier, and in some situations, it's easier to add the factor 8x, because that is clearly what is missing for the complete limit. Yes, we could simply multiply by 8 and divide by 8 without x. Could you please switch off your microphone, because there's this echo?
Oh, yeah, sure.
So yes, we could do. Let me see. I will now. Sorry, I'm clearing your annotation. So what you were suggesting was take the. Let's see. Close and go back to this. What you were suggesting was having this. Okay. Having this limit of sine 8x over 5x, simply multiply and divide by 8. That's perfectly fine, because the 8 divided by 8, of course, it's 1. And then you can see, all right, this is 8x combined with this would give you the 1. And then what remains is, of course, 8/5. That's perfectly fine. And yes, many people do it like this. I am doing it very slowly with those X things for the sake of those people who have never seen serious limits before, because many programs at school introduce limit at a let's say, an intuitive level without using much of limits, just as much as it's necessary for the derivatives. And we are exploring limits in more detail than many school programs, and therefore I am just showing the general idea. But yes, you are right, it's perfectly fine to simply, okay, x is already there, we have 5x, but we really need 8x, so why not multiply by 8? Just 8. So
Yeah,
instead of 8x,
yeah, miss. The thing is, I had I had I had this in school. That's why, because my school did it this way, and I find it
yes,
easier to
I
understand.
know, but there are schools who do not do
I
anything.
understood, miss. Miss, but if I use this method, will I have problem?
No, it's all right. As long as you show what you are doing, it's fine.
Okay, sure.
We will see, in fact, a couple more methods for this limit. These days, there's one more, and of course, towards the end, there's always L'Hopital's rule, which can complicate things if the limit itself is complicated, so the differentiation will be somewhat complicated for some people. So yes, we can multiply by 8x and divide by 8x, or we can multiply simply by 8 and divide by 8, because x is already there. If x is not already there, then we will need the x. We will need to introduce the x to see what is going on. But in principle, what we have to remember is that inside the sign, that expression is not changed. We do not change that one, because that would cause problems and difficulties. We can change things outside sign. We can multiply and divide the fraction, the expression, by the same number or by the same expression. What you choose to multiply and divide by depends on how you think. That's again something else. As long as you don't try to change sine of 8x, because, well, although that might be possible, it would be in some cases very difficult. Another example, tangent x over x. Now let's remember that tangent is sine divided by cosine. So instead of tangent x, I could write sine x divided by cosine x. And now we have to remember one thing. Cosine of 0 is not 0. Cosine actually does not influence, does not affect this limit at all, because in principle, cosine of 0 is 1. So limit of cosine when x tends to 0 is 1, which means that this is not a problem. This tends to 1, so we still have the same limit, sine x divided by x. And so it's still 1, which means from now on, you don't have to do this tangent x to x as split into sine and cosine. We can consider this as a proved, again, identity. So we have sine x over x equals 1 when x tends to 0, and tangent x divided by x also equals 1 when x tends to 0. So we will take it for granted. We will not have, you don't have to repeat this for every tangent you see. This is, let's say, a set limit, a formula if you like. So these two identities, these two limits can be used in a way similar to what you did here. You can multiply by 8, divide by 8. No need to multiply by 5, but by 8, because it's the inside of sine. You can do the same approach for tangent. And yes, you can multiply by 8x, divide by 8x, or simply by 8. They multiply by 8 and divide by 8. That's not a problem. as long as you see very clearly for yourself that you have obtained a limit which equals 1, and then the rest can be simplified. So next page, I'm repeating this. So in this situation, I can make another illustration. This can be illustrated in a different way. For example, if we take the sine function, this is 1 and this is pi. The sine function, you can actually see it from the graph. The sine function actually is very close to the graph of y equals x. So when x becomes very, very small, you see how these two graphs basically join. They're basically the same. They cover each other only for very small x values, of course. For very small values. That's let's say this is another illustration to the fact that this is actually a true limit, which means when x is 0, not only both of them are 0, but when approaching 0, the graphs are behaving similarly. They are very, very similar as graphs. It's not just they are both approaching 0, but they are very, very similar, which makes us think, remembering inverse functions and symmetry, remember that arcsine, the inverse sine graph, is just symmetrical with respect to this very same line. So that would mean that the arcsine graph is just as close to the graph of y equals x as the sine graph, which means that that limit should also be the same. Arcsine x divided by x should also be the same, because the relation between graph of y equals x and graph of sine function is such that they are very, very close here, close to the origin. But because of the symmetry, the arcsine graph also is very, very close. This would be the arcsine of x, which means we actually have another limit. Arcsine x divided by x is also 1. It can be proved analytically. We can, in fact, prove it using algebra, that this would be the same, but we will not do that. It's just, I would hope that the geometrical illustration is enough. Then, similarly, for the tangent graph, we can consider, for the tangent graph, let's remember the tangent graph looks something like this. Approaching pi half, it goes to infinity, but approaching the 0, approaching the origin, it again does the same thing. With respect to y equals x. With respect to y equals x, it does the same thing again. It's again simply very, very close. The graphs practically are the same for very, very small x values. Of course, if we zoom in, we would see they are not really really the same. But as we zoom in and in, we would still always see that as the closer to the origin we go, the more we see these graphs tend to cover each other. But for this, what does that mean? That means that the arctangent graph, again, due to symmetry, right? Arctangent graph, again, goes very close to the same bisector of the first and third quadrant. Again, the same thing because of symmetry. If the tangent graph is very close to this line, y equals x, then arctangent graph, which is symmetrical about that line, also goes very, very close to that line. So that gives us another formula. Arctangent divided by x when x tends to 0 is also equal to 1. So maybe surprisingly, maybe not, but we see that the graphs are very close, and so we have this. So we have a set actually of 4 formulas for special limits, and they all can be used in the same way, in exactly the same way. If you have, for example, limit when x tends to 0 of, let's say, arc sine of 6x divided by, let's say, tangent of 4x. Now this, okay, I'm sorry, it's all red. It's very, maybe difficult to see for some. Okay, so if we have a limit, for example, like this, I know that in the same way, arc sine of t to t equals 1. So for 6x, arc sine of 6x, I would need 6x below the line. So I have to write 6x above the line as well for multiplication. Now I see that this limit will be 1. But for tangent 4x, I need 4x. And of course, if this limit equals 1, then the limit of the reciprocal, when we turn it upside down, of course, it would also be equal to 1. This also tends to 1, of course, when we turn it upside down, because it's 1. Because it's 1. And so for tangent of 4x, we need 4x, not 6x. So we have 2 possibilities. We could write 4x and 4x as I did before, or as Akash advises, just write 4. Just write 4. No problem, because see what happens. We can take this as 4x and tangent 4x, and these combined again tend to 0. So what remains is 6 and 4, 6 over 4, or 3 halves, or 1.2, or 1.5 if you like. We can adjust these things. So if there's no x, all right, we can multiply and divide by x. We can multiply and divide by the same number. It's all that is necessary is an understanding that we can combine certain elements of this expression, and we say, all right, this limit is 1. This limit is 1. So what remains outside is 6 over 4. So in many cases, you can see that when just looking at the given example, just looking at the given limit, in many cases, yes, you can predict what the answer is going to be. That's very good, because then all you have to do is a quick check or a quick writing to make sure that everything is correct, and that's it. So in many,
Miss,
yes.
So, but Miss, is it be easier if you just like if you want to make the bottom 4, it will be more easy if you just multiply the denominator alone with 4 divided by 4, and the top part alone, the numerator alone, with 6 divided by 6, or else it will be confusing, right? It will be easier to understand, right?
Maybe, but we do things. Let's say the things for you. You can do whichever way it is easier to understand for you. If you understand what is going on, it's not. I'm explaining how things work, how you write. That might be a bit different. Right now. I'm focusing on the thinking that we need to find the correct combinations. We need to find the correct combinations. How we write, whether we write 4 at the beginning or at the end, it's really not so important at which end we write 4, at which end we write 6 and x. Also, as I said, there will be another method which I hope you will prefer, because that makes things ever so much easier. So there's one more method when we deal with comparison of infinitesimals with equivalence, where you can substitute something by something simpler. Then that's, I hope, something you will like even more.
Right, miss.
Okay. So now we have another limit. Sometimes we get squares. Sometimes we simply get squares. So there are, let's say, two possibilities. Let me check what the next is going to be. Yes, for this, okay. Sometimes we get squares, not sine and x, but squares. So again, there might be this temptation to multiply by, okay, 3 or 1/3 or something. But in principle, when you have both squares, if you have both squares, one possible way of thinking, again, not necessarily of writing, but thinking is, okay, I could take x divided by sine of x over 3 squared. Instead of the ratio of two squares, let's take the square of the ratio. And now for this, evidently, we need x divided by 3. So we could say, let's multiply by 1/3 and divide by 1/3 if you like. Okay, that would be all right. I will write it more slowly, because if I write things too close to each other, then it is difficult to read and understand. Okay. So when I'm writing this, limit when x tends to 0. Now to get this x over sine x over 3, I would like to have x over 3. So I could say, let's divide by 3 and multiply by 3. There's no need to introduce another 1/3 in the denominator. There's no need. In the numerator, I would like to divide x by 3, and then if I divide x by 3, I can multiply it by 3 again. And of course, all that is squared. And now we see that, again, we see this limit is actually 1, because now we have t and sine of t, but what remains is 3, but the 3 is squared. So this limit is 9. So simply taking the square out is one possible solution, one possible option. However, it's not always that we have this perfect square in the numerator and perfect square in the denominator. Sometimes we have some slighter difficulties, and that's our next example. Another one here. Well, this is not exactly the same. 6x squared is not 6x squared. So it's 6 separately and x squared separately. So there are options again. I would say that some people would do it, well, the way I might advise for people who really are dealing with limits for the first time and want things as simple as possible for their understanding. Not simple for writing, but simple for understanding. There are two different things. Simple for understanding or simple for writing, even though the writing is longer. So, or shorter. So I would write it like this. Instead of sine square of 4x, I would write sine 4x times sine 4x. This is for those people who don't find limits easy. And then we would say, okay, it's 6 times x times x. I spread it out. And then it's very easy for me to see how to deal with this. I need 4x. Okay, I multiply by x and I divide by x. I need 4x for the other sign. Okay, I multiply another time by x by 4, divide another time by 4. So now I see this is 1 and this limit is 1. So what remains is 6 over 16 or 3 over 8. So that would be, let's say, simple thinking. That would be simple for thinking, maybe a bit longer for writing. Then, of course, some other people who want to do it differently might do it also. As I said, there are many ways of writing things down. The basic idea remains the same. We are adjusting the numerator and denominator so that it fits our limit, but how exactly we do it might depend. For example, in this case, you could think it's 6 times x over sine 4x squared, taken things separately. And then you would multiply by 4, divide by 4 inside the square, and you would see what happens. So if you use different color again, multiply by 4, divide by 4, this would approach 1, this would be 1, and so we have 1/4 squared. So we have 6 times 1/4 squared, which is, of course, again, the same thing. So the way you decide to write it depends on you. Just make sure you understand that 6 is not inside the square of x. It's not 6x and squared. So in principle, there are other ways of knowing, guessing, understanding what the answer should be, which are, let's say, with a bit of experience. I know that some people can develop these understandings, so looking at the limit and being able to figure out the answer very quickly. And the longest part is writing down the solution, at least something in between to explain what is going on. But basically, one of the simplest approaches, simplest from the way of thinking, from the manner of thinking, is spread out the squares. Spread out the squares, and then you will see what else is necessary. That would be about the squares. And now, okay, we will have some more special things. So yes, an example could also be, for example, an extra example. Let's say limit when x tends to 0. Let's say x sine of 7x divided by, for example, arctangent of 2, arctangent 2x and tangent of 3x. For example, we can have this kind of combination, a horrible limit consisting of many factors. However, we simply build up slowly the things that we really need there. We understand, okay, we have x. Let's see, for arctangent, we need 2. So we could say, okay, for arctangent, we need 2. That means I multiply by 2. Now I will have this limit, but then I also have to divide by 2. So, all right, one limit is already taken care of. 1 times. Now let's see for the next. For sine 7x, we need 7x in the denominator. That means I can multiply by 7x in the numerator as well. So, all right, it's this. It's also approaching 1. Nice. Now for tangent 3x, I need 3x. I have 7x. So I could write 3x up in the numerator and 3x below in the denominator, or I could write just 3. I could just say, okay, times 3 times 3. So now we have, now I do need to change the color. Now I have 3x and tangent 3x, which also tends to 1. And now I see, what do we have remaining here? What do we have remaining here? We have 7 above the line, nothing else, just 1, 1, 1. And below the line, we have 2. And we have 3. So it's 7/6 in the end. So in green, I did write In green, I wrote the original limit, and all the other colors, the yellow and the red markings, they are for to show what we are doing there. So in green, it was the original limit. So even when we don't have enough x's, you remember that you can, the cure for all troubles, the cure for all troubles here is that you can always multiply the numerator and denominator by the same number or expression. What do you choose to multiply by? How you organize your work? It is all up to you. But the thing is that what we want to do is we want to construct, we really want to construct one of our limits, one of our familiar limits, sine x over x, or sine t over t, tangent t over t, arc sine t over t, arc tangent t over t. Instead of t, of course, we need identical expressions, and of course, they can be turned upside down because one reciprocal turned upside down is still one. So it doesn't matter whether we have sine x divided by x or x divided by sine x. So in this case, it was turned upside down, but it's still one. One upside down is still one. And we just adjust the limits by symmetrically in a balanced way, adding more terms, more factors, but identical factors in numerator and denominator, in order to be able to cancel out the limits that are equal to 1, to just get rid of them. Now, another trigonometric limit. Again, there are at least 2 different ways of dealing with this, probably more. Oh, 3, 4. So you see, there are more ways of dealing with it. I think off the top of my head, I can think of 4 different ways for resolving this limit. Just remember that cosine of 0, that's something I already reminded you of. Cosine of 0 is 0. Sorry, not 0, it's 1. Sorry. Cosine of 0 is 1. So we have 1 minus 1 is 0. X squared, 0 squared is 0. So this limit is still 0 over 0. It is still 0 over 0. However, it is not the same as previously. We don't have sine of something. We have 1 minus cosine. So what we need to do is we need to rearrange this expression so that we see one of our familiar trigonometric limits. The simplest way, well, there are 2 simplest ways of doing this at the moment. So one way is, if you know trigonometry really, really well, and if you know how to change this expression 1 minus cosine something into something different, into the sine of half angle, then of course it works. If you know enough trigonometry, if you know the key formulas for dealing with double angles and half angles. If not, then classically, because it's also reminding, it can also remind us of some other limits that we have already done before. What if I multiply by the conjugate sum and divide by conjugate sum? What happens here is in the numerator, when I open the parentheses, I get the difference of squares. 1 square minus cosine square. So it's 1 square minus cosine square of 5x divided by x squared. I'm not opening the brackets down there below the line. So now 1 minus cosine square is no more nor less than the sine square of the same angle. of the same angle with 5x, including. And so we have x squared, and here we have 1 plus cosine 5x. Now, to remember that because cosine x or cosine 5x tends to 1, when x tends to 0, the parenthesis 1 plus cosine of 0 actually approaches the number 2, because in principle we could see that this is actually 1 plus 1. Cosine of 0 is 1. So as we write, we could see that this is evidently, first of all, 2 goes in the denominator. So I can bring this 2 outside. I can bring this 2 outside. And then I would say limit sine square 5x divided by x squared as x tends to 0. 25 halves is right. 25 halves is right. So we can think, again, it's a bit longer. I am writing down the way we think. We don't always write this way, but we think, as in this case, I would say it's sine of 5x divided by x, all of it squared. So I would need to multiply by 5 and divide by 5. So times 5, divide by 5. So this would work out. This part would work out nicely. So I have 1/2 times 5 squared, evidently. And so it's 25 divided by 2, or 12.5. So the thing with 1 minus cosine something in these trigonometric limits, one way of resolving it without having to memorize any difficult formulas is indeed to multiply and divide by the conjugate sum, which automatically, according to trigonometry, automatically creates sine square. Automatically, we create the sine square this way. But of course, we have this extra factor in the denominator. However, when x tends to 0, this extra factor very nicely, obligingly, tends to 2. So we have 2 in this case, in the denominator. Sometimes it happens upside down. Sometimes we have this difference in the denominator, and then we have 2 in the numerator. So this is one way of doing this. This is one way of doing this. Another way, which might be difficult because then you really need to keep track of all the formulas. Another way is using the formula sine square alpha 1/2 is 1 minus cosine alpha. Oh, okay, I can actually do this. So this is sine square of a half angle, the formula for the half angle. So we can in fact use this. We can use this, or that would mean 1 minus cosine alpha is actually 2 sine square of alpha. So we can actually move to an angle that is 2 times less. That would mean that here, instead of this, we would have 2 sine square of 2.5x. And that might cause problems if we have an odd number. If the number here, instead of 5, if we have an even number, then of course half alpha would be nicer to write. But in this case, we would have 2 sine square, but of half of 5x. So again, we would still be able to resolve this limit. This is simply an alternative approach. But I would say that much easier to remember is just this formula for 1 minus cosine square equals sine square of the same angle, because we have already been multiplying by the conjugate sum, multiplying and dividing by the conjugate sum. So we can say this is one pretty universal traditional method that is not so difficult to remember, memorize, and it can be used in different situations. So there's nothing wrong with doing this. It's, let's say, maybe not the shortest, but definitely from the manner of thinking, the easiest way for now. So 1 minus cosine something, generally, the simplest approach would be multiply, divide by the conjugate sum. Another alternative approach, use a formula for the half angle, change it into sine square of half angle. And yes, we will have a coefficient 2 then, using this formula, always possible. And then there are more approaches, which will be discussed later. So for now, these two. One more. So today we will be dealing with this limit. I would say I'm not going into the other one. So what happens is, okay, I'm checking the time. Oh, we still have time. That's very good. We will go as far as needed. Okay. So 1 minus cosine cube. 1 minus cosine cube is not something very nice, because we know what to do with 1 minus cosine. So what should we do with 1 minus cosine cube? Because with a cube, the conjugate sum might perhaps not work. But we still have this situation where when x tends to 0, cosine tends to 1, we still have 1, and we still have 0 divided by 0. So the first thing to do in this case, would be, perhaps we need to use one formula from algebra. Remember, perhaps in algebra at school, we had formula for the sum of two cubes, for factorizing the sum of two cubes, and for factorizing the difference of two cubes. It was the sum of the first power, first degree, and times the incomplete square of the difference. So a square minus ab plus b square. Incomplete because the number 2 is missing. It's not the perfect square, it's incomplete. And for difference, we have the difference of a and b and the incomplete square of the sum. So see how only two signs differ. So if I have plus here, then I have plus in the first parenthesis and minus in the second. And if I have a minus, then I have a minus in the first parenthesis and quite differently plus there. So the squares always have plus in front. A square is always positive. B square is always positive. And AB is opposite to the sign in the first parenthesis and in the squares. So this is something that generally in high school, this formula is supposed to be known and familiar, which means now I can factorize 1, think it's 1 cube, 1 cube minus cosine cube, so that would be 1 minus cosine x times 1 plus cosine x plus cosine square x, using this formula, using this second formula of difference of cubes. So I could imagine that some of you might have forgotten this formula from school, maybe, but this is something that after high school you're supposed to know. And then we have x sine of 2x. And now let's think. When x tends to 0, 1 plus cosine tends to 1, and then cosine square also tends to 1. So the total parenthesis actually tends, the sum in the parenthesis, this taken together, actually tends to 3. So we can take 3 in front of the limit. We can take 3 in front of the limit, and then inside the limit, we have 1 minus cosine x divided x sine 2x. So we can basically again do the same thing. Or if you like, we can try that formula from trigonometry where 1 minus cosine alpha is actually 2 sine square of half alpha from trigonometry. If you like, we can try this. We can try this as a trigonometric formula. So I am not multiplying by, we could multiply by 1 plus cosine x, divide by 1 plus cosine x as before, but this other approach could be perhaps just as nice. So we have 3 limits when x tends to 0. 1 minus cosine x becomes 2 sine square of half x divided by x sine of 2x. So now I can take 3 also outside. Limit, now we have 6 lim x tends to 0, and in here we have sine x half, sine x half, maybe that's a little bit easier, x sine 2x. So I would say if I divide this by 2, then I also need to multiply by 2. So one of these is already taken care of. Now I want x half. There's nothing like x half here. So I would write, all right, x half here and x half up there, if you like. Again, to make sure that things fit. And now I have 2x, I have x half. So I need to multiply by 4 to get 2x from x half. To get 2x, I need to multiply by 4 and divide by 4. So now this is again 1. So what do we have here? Is 6 and 2 times 4 over 8. So it is 3 over 4. In principle, this is just as well. So I am simply reminding you of all the variety of approaches we might have. It depends on how well you understand trigonometry, how well you remember trigonometry. In this case, it's of course also important that you know a couple of high school formulas that are important. But in principle, we could do it like this, or we could do it by multiply by 1 plus cosine, divide by 1 plus cosine, and work things out perhaps faster, actually, in this case. So this first approach would have been faster. We would have 3 limit 1 minus cosine square x divided by x sine 2x 1 plus cosine x as we multiply by the conjugate. So this is 2 in the denominator, so we have 3 halves lim sine square x divided by x sine 2x. And this is comparatively simple if you spread out that sine x, for example, or if you remember trigonometry, sine of 2x has a formula. So you see, it depends on what you see in the limit itself. What you see, what you recognize as something that you can use. In this case, we say, okay, sine 2x, and everything else is just x. So I might want to use the formula for sine of 2x. I do hope that you remember it. X tends to 0. X tends to 0. Oh, people coming very, very late. Sine x, here we have x, sine of 2x by formula is 2 sine x cosine x. Should remember this formula from school. So these cancel out. This limit is 1. Cosine tends to 1. So we have 3 halves divided by 2 divided by 1, and it's the same again, we have the same answer. So in general, you never know which approach might turn out to be the best. In principle, I myself do prefer this multiplication by the conjugate. Multiplication by the conjugate factor, because that way it's, let's say, it doesn't require me to remember so much trigonometry. I do remember it, but when I'm writing very quickly, sometimes this is faster for me. But it depends on each one of you. So trigonometric manipulation is important. And as I said, next Wednesday, we have the elementary mathematics test number 3, but we will also start trigonometry next time in elementary mathematics. I had some more limits. I had some more trigonometric limits. Now in this, we have like 0 minus 0. What doubt is there? And 2x cubed, who might think what is going to happen here? What kind of limit is this? Is this limit equal to 0? Is this limit equal to something else? That sometimes creates a little bit of difficulty because it's not immediately clear. Although it might seem so. So we need to transform this limit. Again, limit when x tends to 0. And now let's see. We have sine x minus tangent. Let's rewrite tangent as sine x divided by cosine x over 2x cubed. I have no idea at the moment. Well, I do, but we in general have no idea at the moment what is happening there. So let us multiply the numerator and denominator by cosine of x. We can do that because when x tends to 0, cosine does not tend to 0. So let us simply multiply. Let's add in an extra factor, cosine x. We would have sine x cosine x minus simply just sine x, that is sine divided by cosine, and here tangent divided by multiplied by cosine. Tangent multiplied by cosine is sine x. In the denominator, 2x cubed cosine x. Now let's remember that cosine actually tends to 1. So in the denominator, we have no problem. In the numerator, yes, we do. Limit when x tends to 0. Now let's take sine out of parentheses. In the parentheses, we have cosine x minus 1. And here we have 2x cubed cosine x. So as a factor, cosine x approaching 1 is harmless because it tends to 1. Now then, sine x divided by x will also tend to 1. So what remains now of this limit? Sine x goes out together with one of these x's. So we have cosine x minus 1 divided by 2x squared remaining. Only this remaining, because sine x and one of these 3 x factors makes the trigonometric limit 1, and cosine x tends to 1. So basically we take out some parts of this. So cosine x tends to 1, so I don't have to write it as a factor. However, in the parentheses, see, this is important because we remember we could transform this to something else. Now we might multiply it by the conjugate sum. We might multiply it by the conjugate sum, so it will be again, I can write cosine x plus 1, cosine x plus 1. Now I am pretty safe taking out some things in front of the limit. That is 2, the number 2, and this is another 2. So 1/4 outside the limit, and what remains inside the limit is cosine square minus 1. That is minus sine square of x. Remember, 1 minus cosine square x is sine square x, but here when we open the parentheses, we have cosine square x minus 1, so it is the opposite. So it is the opposite. So that's why we have minus sine square x up there and x square. Now we see it's minus the square of sine x divided by x. So we could say minus 1/4 limit when x tends to 0. Don't forget the minus. And sine square x divided by x square, we think, not necessarily right, but if you understand, you would be able to write. So sine x divided by x, limit is 1, squared, still 1. So the final value of this limit is minus 1/4, and not 0 as we might think at the beginning. Not 0 as we might think at the beginning. So it's perhaps a slightly strange and slightly unexpected result. Nevertheless, so not always things work out very obviously. In many cases, the result can be slightly unexpected. Slightly unexpected. So in this case, the reason why we cannot say, okay, we could split it into 2 limits, sine x divided by 2x cubed, tangent x divided by 2x cubed, but as a result, it would be basically infinity minus infinity. So we cannot split it into 2 limits. What we have to do is we have to manipulate it until everything is clear. In limits, the preferred form is factorized. Everything as a product or quotient, but everything factorized. So factors in limits are much better and safer to use than terms that are added, subtracted. Basically, our aim is to factorize as much as possible. Factorize as much as possible, turn everything into a product as much as possible, and then the limit is, let's say, we are safer to say that the limit will be correct. In this case, I worked hard, you see, to factorize this as well as I can. So this factorizing process was important. Not just sine minus tangent. Yes, sine minus tangent would be 0. Would be 0, but as such, by itself, it's not useful. Factorizing is the key. Just like in algebra, when we want to simplify rational expressions, factorizing is the key. Similarly, in limits, basically, factorizing is more useful than anything else. All right, something somewhat similar. One more. How much time do we have? We have, I guess. All right. I think I will leave these for the next time. I will leave these last things for next time for the sake of revision, for the sake of quick revision, because it's, on the other hand, it's not so very good to just remember one topic, one lecture without revision. So next time we will do the remaining examples, the remaining exercises. But today we will start the second special limit, which deals with the indeterminate form 1 to power infinity. And you might ask, what's the problem? 1 to power infinity, why isn't it 1? But the thing is that with these things, we will be dealing, for example, if you consider a limit like this, we might think, okay, when x tends to infinity, 1 divided by x tends to 0. So the base here tends to 1, but x tends to 0, x tends to infinity. So the problem is the base tends to 1, but it's not ever exactly equal. It's always, as you see, for example, if x is positive, is always slightly more than 1. And if you take many, many, many factors, x tends to infinity, the power is great, many factors like that, then something not exactly 1 to a very large power, but something slightly greater than 1 to a very large power will evidently be also greater than 1. Or if it's what now? And if x is negative, then we have again something missing from 1, a little bit less than 1, and then we take the power. So in principle, when we write 1 to power infinity, we of course don't mean the exact expression. When we talk about limits, it's indeterminate form because we don't understand 1 as the constant 1, but we understand 1 as something that tends to 1, but is not exactly 1. So we have a problem with this. To investigate, let's have a look at the values of this expression. What happens to this expression when x becomes very, very, very large? Something that you don't have to copy because you have it in your lecture transcript and it's just a table of values. I made an Excel table of values and then I copied it to this. Excel table of values for some x, 1, 5, 10, you see that these values are increasing. It can be proved that this expression, that this function is actually increasing for positive values of x. It is increasing, and at the same time, the values are between 2 and 3. That can be proved, that this series or the sequence, actually, this function is increasing. At the same time, it is bounded. It never becomes greater than 3. In principle, we see the first x values I took comparatively small, and then I increased them faster. When x is 5,000, see what value we have, 2.718 and something. The thing is that you see that the difference between these values becomes smaller and smaller, even as the distance between x, the leap of x, the step of x increases, the difference between the subsequent function values decreases. So the values of this function seem to crowd towards a certain value. This value, so we in general say that this limit exists, 1 plus 1 over x to the power x when x tends to infinity. This limit exists. We cannot evaluate this number exactly, but it exists. So we call this number e. And this is where the magical number e, the magical value of e, comes from. There are other ways of finding e. So one way would be just make x values very, very large, and you will get an approximate value of e. But of course, you have to make sure you understand how accurately you round this, how precise your value actually is, to how many decimal digits should you write it out. There are other ways of finding e, but in principle, e is, let's say, a magical number, the magical constant, 2.718281828. It's not a repeating decimal. It's not periodic. So it's not a rational number. It's irrational. And as such, it cannot be written down as a finite or even repeating decimal. The magical number e. So this is where the function e to power x comes from. Remember, we used it to discuss the hyperbolic cosine, which was e to power x plus e to power minus x divided by 2. The hyperbolic sine, which was similar, but the difference, we discussed this sometime last week. I would say. So this is where the exponential function e to power x comes in. It's very, let's say, important in mathematics, this function e to power x. It is unique in some ways. We will return to this when we discuss differential calculus. We will return to this function. It has interesting properties, and as such, it plays a huge role in mathematics and also physics, by the way. And another way where we are using e, that would be natural logarithm. Logarithm to base e is generally written as ln of e. Somebody has microphone switched on, please switch it off. So ln of e, the natural logarithm of e. I want to remind you that expression simply logarithm of x is not accepted, because in some textbooks, by log x, the author means decimal logarithm of x, and in some other textbooks, the author means ln of x by logarithm without the base, when they don't write base. So we always, either we write the base, or we write ln if we mean the natural logarithm, or lg when we mean decimal logarithm. That's a reminder for those who do not take elementary mathematics. I did mention this in elementary mathematics, but for everybody, log without base, we are not accepting log without base, because it can cause misunderstandings and difficulties, because it can mean different things by different authors and different textbooks, and therefore we don't use that. So logarithm is, of course, the inverse function of this exponential logarithm.
So we have to use, like, if using if we taking log base 10, which is just log, we need to write log base 10. We can't just write log.
You can write log 10, or you can write simply LG, which is shorter than log. Just log, in some textbooks, it means ln, and in some other textbooks, it means LG. Therefore, either write the base or write LG. And here the same, either write the base E or write ln. ln is also internationally accepted. LG is perhaps less known, but still it is accepted.
Yes, miss. So we can't use log alone. That's what you mean.
No, yes, that's what I'm saying. No log alone, because by that I can understand this or that, because I have seen both kinds of textbooks. Okay. And if you do that, I will make a point by choosing to interpret in the wrong way. That's so that there's more fun for you. Okay, so how do we use that kind of limit? All right, so this limit is E. And once again, so how can we use this kind of limit? So it's one and only. But okay, I will start with this. We will be able to, again, for the sake of revision, to discuss some slightly simpler examples next time. So in this case, some preparation. So x minus 1 divided by x plus 3. Of course, when x tends to infinity, then this actually does tend to 1 when x tends to infinity. Of course, if you take x in front, the factor x in front, cancel it out, you will see the limit actually is 1. So we need to somehow rearrange this so that we get 1 plus 1 over t to power t. Then this kind of limit, again, that would be e. The limit of this would be e. So the problem is, how do we change this into 1 plus 1 over t? So it's, in principle, it's comparatively simple. One way is polynomial division, if you know how to divide polynomial by polynomial. And the other way is, if I have x plus 3 over x plus 3, then this is 1. I don't have x plus 3, I have x minus 1. So to get x minus 1, I need to subtract 4. So I simply change this expression into this form. I choose x plus 3 so that I can divide these and get 1. And of course, I have to write the correction minus 4 because I need to keep the same value. So this is 1 minus 4 divided by x plus 3 now. Okay, so there we go. The limit when x tends to infinity, 1 minus 4 over x plus 3 to power x plus 2. This is our last example today. So next time we will discuss more details about this second limit. But now, what do we do now? So we would like to get a limit in this form. So what we do is we force it. We say, okay, we have, instead of plus 1 over t, I have minus 4 over x plus 3. Okay, I say, let it be so. So let's rename, we simply rename this expression to 1 over t. So please note that the minus is included because the formula requires a plus. And of course, we see that if x tends to infinity, then t also tends to infinity. That is also true. Let's go back to white. And so now I can rewrite this. When x tends to infinity, I have 1 plus 1 over t now, because I renamed that wrong fraction which means now I would need t. Okay, so I will do another neat trick. I want t for the limit, and remember the mathematician's nature. If we want something which is not there, we put it there. But of course, it's not correct, because actually the exponent should be x plus 2. So if I multiply by 1 over t, now this is 1. And then I multiply by the actual exponent. So let's see, I put t in there because I want my standard limit, but it's not the correct exponent. So I immediately multiplied by 1 over t so that this doesn't hurt. It's now the exponent 1. And I multiplied by x plus 2. X plus 2 is the actual exponent that we had there. Now let's see what we get now. Limit when x tends to infinity still. Now pay attention that, first of all, this is actually t. Not t, sorry, it's e. So it's e. So we have e. Instead of this, the limit of this is e, but it's taken to this power. So, all right, 1 over t. Now let's check. 1 over t, it's this. This is 1 over t. So I can write, instead of 1 over t, now I want to combine these to get the correct exponent at e. 1 over t is minus 4 divided by x plus 3. And I have to multiply it by x plus 2. So in fact, I take 1 over t and I put it in there. And so this means that basically I need to find this limit, and the limit of this will actually be the exponent for e. So now again, I can do a little bit separately somewhere. The limit of minus 4, I can take minus 4 outside actually. And so I might have just x plus 2 divided by x plus 3 when x tends to infinity. and I see that it's minus 4 times this limit when x tends to infinity, dividing out. Now I'm reminding you how we find these limits. Dividing out x from numerator and denominator, we have 1 plus 2 over x, 1 plus 3 over x. That's, of course, 1. This limit is 1. So minus 4 times 1 is minus 4. So this is e to the power minus 4. Or rewriting it normally, algebraically, without negative exponents, 1 over e to the power 4. So this is, let's say, the worst that can happen with this kind of limit. The worst that can happen. First of all, we see a horrible fraction in parentheses, and it's taken to power again, including x. We have to work to change this into something acceptable. Next time, we will start from simpler equations again, from simpler examples, from simpler limits, moving towards more complicated limits, moving towards this once again. So we will take a step back and start from simpler limits next time. Don't worry that if this seemed too difficult at first, next time we will take a step back and start from simpler examples. Now, administrative issues. As administrative issues, people who came late. I did send the link to people whose email addresses I recognized in my address book, because I could not access the eStudies server either. So I had to use my Gmail address book. That's one thing. Another thing, if you did not receive the Zoom link, I did not bother to include people who generally do not attend lectures. There are people who consistently do not attend lectures. I am not going to cater to them. You are in deep trouble if your attendance is below 50% during this time, and I know who they are. So I'm not even bothering to send them anything at all. They have failed the course already. And I'm saying this because I recognize a few people like that here at the moment. I wouldn't say that to general public who are not guilty. Now, for the nearest future, first of all, on Friday at 12, we can arrange a retake for elementary mathematics tests 1 and 2. Friday at 12, evidently I will be there, and we start with number 1 and then we move on to number 2. That's Friday at 12. Then Friday, this Friday in 2 days. Then Friday, so we have lecture from 2:30 to 4. So Friday at 4:30, we can retake unit tests. Unit test 3 generally, and unit test 2 after that. Again, for separate people. Midterm retake next week sometime. I still have to think, because all these people who don't come to lectures or come to lectures but do not come to the tests do not deserve any favors from me. So one thing, the unit test number 4, the limits test, unit test number 4 for limits is going to take place next week. So on Friday, we will finish these limits, these special limits, and have a look at the comparison of limits. Next Wednesday, we will have a look at continuous functions, or maybe start the new topic. And then next Friday is May the 7th. There will be the unit test number 4. However, seeing what happened with unit test number 3, less than half turned up to take unit test number 3, and then they started whining about retakes and extra times. If you do not show up for a unit test at the appointed time during lecture, and you have not announced, you have not let me know before, and you have not provided a document confirming that you cannot really attend that unit test, then the retake will be highly dubious for you. Because what I saw during unit test number 3, the original unit test number 3, was that only about half of all the group turned up for the unit test during the regular lecture time. This is unacceptable. Those people do not deserve retakes. You think, okay, I will wait, I will not take it during the lecture, and then I'll see what was there, I will learn from my friends, and then I'll go to the retake. No way. No way. I'm really angry about this. So in the future, if you miss the unit test in class, I need a documented confirmation about the reason. That's it. That's it. You are slacking too much. You are slacking too much. I apologize to those people who do everything as they are supposed to do. You don't deserve this anger. This is not for you. So next Friday, we will have unit test number 4, and beware. If you don't attend it, you should provide documented reasoning, not just not turn up. Next, maybe a nicer thing. On Monday, May 3, I couldn't put it in Ortus today because you as you saw the webpage was unavailable. May 3 is a bank holiday in Latvia, which means basically that Monday's schedule is moved to Saturday, the 8th. Okay, I shouldn't write with the mouse. So May 3 is a bank holiday, which means you are going to have a long weekend. The first Saturday, Sunday, then Monday, and May the 4th is again a national holiday. So this is why May 3 is moved to Saturday, so that you can have a long weekend, or we all can have a long weekend. We have a long weekend, 4 days, May from the 1st till the 4th of May. But Monday schedule from the 3rd of May is moved to Saturday, the 8th of May. As soon as I can access the Ortus webpage, I will put up a notice. So the our next lecture is Friday, this Friday, as usual. But then on Monday, you have a free day, but we have to work on the 8th. We have to work on the 8th of May for that. And so that's why the scheduling is a little bit messy. I will put up notice with the schedule as soon as I can get into Ortus webpage. For now, Friday, that is in 2 days at 12, we will have elementary mathematics retakes, and in the afternoon, the unit test 2, 3 retakes for those who need access to midterm examination. For those who need access to midterm examination, for those who have not written it. And then next week, someday, we might have the midterm repeat, or rather the midterm for those people who have not written it yet, who couldn't write it for a variety of reasons. And then we will see how things proceed from there. So the nearest things that you need to know is that on Friday, we have retakes at 12 and at 6:30. Then Monday after that is free. And then the week will proceed further on. So the nearest things, Friday retakes, Monday free. That's about it. That's about it. So I will see elementary mathematics people in about 15 or 20 minutes. I've been talking a lot, so maybe we'll start slightly later. The link was sent to you in the email. If Portus is still unavailable, I don't exactly know. Let me